So, good morning everyone. Thank you for coming. It's good to see so many people here who are curious about Swift. At least I hope you're all curious about Swift. It's a very deliberate choice of words in my title that I selected because I wanted to try and appeal to people who aren't necessarily intending to write Swift. Always keep an open mind, of course. But I think it's a healthy attitude as a developer to keep an eye on other technologies or languages, see what's going on. And particularly a language like Swift, which certainly in the Apple ecosystem is becoming really important, as we'll look at a little bit later, and how that might sort of leak out into other ecosystems as well. We'll touch a bit on that. So we are going to look a little bit at the context and history that Swift exists in. But that said, the majority of this session is going to be live coding. I want to show you what the language looks like and how it feels. And the nature of live coding, of course, is it's a bit unpredictable. I've got 7 demos to get through here. Most of them are quite short, so don't let that put you off. But remains to be seen if we'll get through all of them, so we'll keep that open as well. So I wanted to start with a bit of the prehistory of Swift to really put it into context. And to really dig into that, we actually need to go right back to the early 80s. Towards the beginning of the 80s, Brad Cox and Tom Love at Stepstone developed a new language called Objective-C, which was basically the marriage of Smalltalk and C to bring OO to the C language. Obviously, C++ was coming along at the same time. There are actually quite a few object-oriented versions of C around. Objective-C is one of the few that survived to this day. And there's a whole story about how Objective-C evolved over the years, which I'm not going to dig into too much. I want to actually track a parallel story that started happening around the same sort of time, and then we'll see how they come together at the end. Because the iconic year of 1984 came. Of course, we're familiar with the book by George Orwell of that name, and Apple in 1984 used that imagery in a video for an advert that they ran in the Super Bowl to introduce a new computer. First time the world had seen this computer, it was, of course, the very first Apple Macintosh. And it's difficult to really appreciate, looking back now, just how revolutionary this computer was as a mainstream consumer computer. It was the first, at least commercially available, graphical OS. It's a graphical GUI first, brought Windows icons, the mouse menus to the masses for the first time, but also had an unprecedented level of integration between the software and the hardware. That's really been Apple's key strength right from the beginning, remains so to this day. For better or worse, people have different opinions on that, but it definitely, in the case of the Mac, really resulted in a complete end-to-end product that was not necessarily that commercially successful at the time, but was definitely highly regarded. So that was in 1984. If you fast forward just a few more years to 1994, the situation actually changed quite a bit. In the intervening years, Steve Jobs, of course the co-founder of Apple, and also the head of the Macintosh team at the time, had been pushed out of Apple. He'd gone on to form his own company, Next. Next actually ended up licensing Objective-C, that's where that comes into the story, and formed the basis of their Next Step operating system. Apple, meantime, were in trouble because their operating system hadn't really moved on very much, and even Windows was coming along to eat its lunch, not to mention OS2 and other platforms. In fact, there were 2 key issues in the operating system arena at the time that basically they weren't solved on these. They were looking to run out, basically. Those 2 issues are preemptive multitasking and protected memory. Turned out to be really tricky things to retrospectively add to an operating system. Apple had a few attempts. Probably the biggest one, the last one, is called Project Copeland. They had a string of projects named after American composers. And basically after a lot of setbacks, by 1996 that project was cancelled Famously, Apple at this point was said to be days away from bankruptcy, unless they could pull off some big stunt, which they did. They looked around for an external operating system and ended up buying Next, Steve Jobs' company. So that's how Steve Jobs came back into Apple. Of course, eventually became CEO again, but importantly to our story, brought the Next Step operating system in, which formed the basis of the Mac OS X operating system, so that the marriage of the Mac OS and Next Step. And that brought Objective-C back in as well, or rather brought it in for the first time. So what does this have to do with Swift? Well, we'll get to that, but a little bit more on this story, because forward on a few more years again, by 2005, a guy called John Siracusa, who, if you're in the Apple ecosystem, you probably know the name. Well, he wrote an article for Ars Technica called Avoiding Copeland 2010. So that's a reference back to that failed operating system project from the 90s that almost cost Apple their business because they couldn't pull it off. He was arguing they're facing another crisis of a similar scale, this time not to do with the operating system, but to do with their main development language. Objective-C was central to the Next Step, but it was really showing its age. And his argument was that if they didn't come up with a replacement, a modern development language, then they were going to be facing a similar problem. That they couldn't head off by pulling something out of the bag at the last minute. They needed to be working on it, well, he said, by 2010, hence the name Avoiding Copeland 2010. Well, 2010 came and went, not a word from Apple, which of course is Apple's way of doing things. 2011 came and went, and so on. But Siracusa actually wrote a follow-up article in 2010 where he revisited this idea. And he basically said that the advent of the iPhone in particular had sort of set the clock back a little bit, given Apple a little bit more time, but his prediction was basically still sound. If they didn't come up with this new language soon, they were going to be in trouble. Finally, we get to 2014. And Craig Federighi gets up on stage at WWDC, the Apple Developer Conference, and says, what if we could have Objective-C without the C? And he wasn't talking about just a variation on Objective-C. He was talking about a whole new programming language, which of course turned out to be Swift. In fact, they even named it at the conference. And even showed us a teaser of some of the features that were going to be in the language. And if you were a developer in the Apple ecosystem at the time, this was a really big deal. Because not only did this language appear to have all of the features we've been asking for all these years, but it went far beyond that as well. In fact, looking at some of these features, we've got quite a few that appear to be coming from functional programming languages, and there were a lot of questions about, is Swift going to be a functional programming language? So we're going to ask that question as well. But that was 2014. A few years have passed since then. How's it looking now? I actually put these slides together originally last year. So next few slides are from the 2016 Stack Overflow Developer Survey. I did go to refresh them to bring the up-to-date numbers, but they hadn't changed that much, and actually it wasn't quite as clear the way they categorise things anymore. So I've kept these ones. Bear in mind that things are slightly different now. But a few of the graphs that I selected from that survey that relate to Swift. First of all, most popular technologies per dev type, in this case mobile. So Swift is obviously important in mobile. And this is technology, it's not just languages. So, we've got Android at the top there. The first language there was Objective-C, but already last year followed closely by Swift. And I believe that has now overtaken it in the latest developer survey. But this is most popular, not in the sense of what people like necessarily, but just what they're actually actively using. So there's obviously a huge legacy code base of Objective-C code bases out there, and Swift is already overtaking it. So that's actually quite amazing, I think. In fact, there we go, there's Swift there. But another chart was most loved. So this is more about what people actually want. And this was just languages. So Rust was topping the list last year. I think that's changed a bit this year. And Swift was already number 2, which is amazing for a language that was just over a year old at the time. F# there is number 3. I'm quite pleased about it. It's one of my favourite languages as well. But what's missing from this list is Objective-C. Where does that come in? Well, there was a most dreaded tab as well on there. And Objective-C is right there at the bottom. I think that says everything you need to know about the developer community's opinion of these two languages, at least the ones that visit Stack Overflow. So the other thing that happened just at the beginning of last year, or December of the year before, was, as promised, Swift went fully open source. And I want to emphasize the word fully, because some open source projects are sort of nominally open source. They'll do code drops every now and then, but the actual development goes on privately. That's not the case with Swift. In fact, the whole Git repository was checked into GitHub. You can actually go back and look at the very first commit made by Chris Latner in 2010. Remember that date. We can see the whole thing there. Not only that, but moving forwards, the development of the language, the evolution of the language, is all going to be taking place, or is now taking place in public, on public forums, and not just between Apple employees, but the whole community is contributing. There are Swift language features in there now that have been proposed and implemented by the community. So this is a true open source project. A lot of people from outside the Apple ecosystem don't necessarily appreciate that. It's obviously initiated by Apple, still controlled to a large extent by Apple, but it's a community language now. That's important. So I mentioned that date. We'll come back to that in a moment, actually. WWDC, the Worldwide Developers Conference, where all the Apple developer news first comes out. In last year's conference, Swift 3 was announced. And the first few versions of Swift, it was actually promised right at the start that they would have significant breaking changes between releases. So it's another reason that it's phenomenal that Swift has got such a wide acceptance so quickly, on the basis that your code's going to be breaking regularly and you're going to have to fix it up. It's been a pain point for many people, but they've been prepared to take that on. But a big push with Swift 3 was to get those breaking changes out of the way as much as possible and stabilize the language, at least at the language level. So there was a lot of breaking changes in Swift 3. And they've achieved a certain level of language stability now. So Swift 4 was announced a couple of weeks ago. We've known for some time what features are going to be in it because it's now developed in the open. And very, very few actual breaking changes. So it all seems to be working according to the plan. In fact, I didn't come back to that date. Must have deleted that slide. 2010 was also the date that John Siracusa was pointing to in his article. And actually, his follow-up article, written in 2010, was 1 month before that first check-in. And the last time I gave this talk, it was just pure speculation. Was that actually a factor? And I said at the time, we'll probably never know. And about a month later, Chris Latner left Apple, and he went on all the podcasts. And one person did ask him, was that a factor? And he actually admitted that it was, on his mind at least, when he decided to start writing Swift. So, yep, just if you're writing for an article on the internet, you can actually change things at this scale. So that's the context that this appears in. I want to get onto some code demos because I really want to show you what the language itself is like. So I'm going to switch over to that now. Let's try and, there we go. And can you read that okay? It's an interesting configuration with the screens in here, so hopefully that's going to be okay for everyone. Now this is something called Swift Playgrounds. It's part of Xcode. And it's a really interesting way of exploring the language and exploring language features or experimenting with bits of code. If you've ever used a language with a REFL before, well, it's like that, but actually takes it even further. And to show you what I mean, if I just type some code here, So just initialize this integer. And you can see on the right-hand side, we've got the evaluation of that code pretty much immediately. Sometimes it takes a little while to catch up, so it's not perfect. So if I write another one here, oops, if I can type. Again, we see that come up immediately. And notice we've got an integer here and a string. I haven't had to mention any types. So first question is this a dynamic language, or is it a static language with type inference? And if we hover over this string here, we can ask it to tell us the type. I don't know if you can read that. I haven't increased the font size for that, but it is telling us that that's a string. So this is type inference. It's pretty good. Better than, say, C++'s type inference, but not quite as good as some functional languages. Okay. Now, we can annotate our types if we want to be explicit. So type annotations suggest that the language is designed from the ground up to expect type inference as the default. You only annotate the types when you need to be explicit about them. So most of the time, we don't do that. We just let the compiler do its thing. There's a lot less implicit conversions between types, so it's usually pretty safe. So what else can we do? Well, let's try and add to that string. Yeah. Let's get our sort of typical hello world. And now we get an error. If we have a look what the error says, if I can move that up. Okay. So it's telling us the left side of the mutating operator, that's the plus equals, is immutable. And it goes further. Str is a let constant. So now that's telling us, well, let introduces a constant. And it even tells us what we can do to fix it. We can change the let to var. And in fact, if I click here, again, that's maybe a bit too small to read, but it's telling us that we can fix it by changing let to var. I know it's done it automatically for us. So it's a really productive environment to explore the language and just mess about with things, really. So we've got let to introduce a constant or a name binding, and then var to introduce a variable. So this is already telling us a little bit about the character of the language. So if you've used some sort of traditional OO or imperative language like Java or C++, C#, you'll know that mutability is sort of the default, and you have to add extra keywords to get something const or immutable, like the const keyword, for example. A typical functional programming language where immutability is the default, you have to add the extra keywords to get mutability. Swift is sort of playing it down the middle. It's just as much syntactical noise to introduce a constant as a mutable variable. So it's sort of saying, well, I don't really have an opinion on this as a language. You do what you think is best, but immutability is important. So that's an interesting nod towards the character of the language. So we do that. Got our string now. Now we've been evaluating strings, but we can print them. We've got a console down here at the bottom. So there we go. We've printed our string. So print is a function. And we could also print our integer if we wanted to. So it will just automatically convert that to a string for us. But if we wanted to put the two together, now we're going to do some sort of string formatting. And Swift has string interpolation. So what we do is we put them, put the variables in round brackets within the string, preceded by a backslash. And we can do that for different types. And there we've got a formatted string. Now because that's interpolated into the string, we're not relying on the print function actually doing this job for us. So in fact, rather than printing it, we can just assign that to another variable. There. When it catches up, there we go. And there we've got a formatted string. It's actually quite nice, quite clean, I think. So, what else can we do? So we have arrays. I won't go into this too much because we'll come back to this in a minute. So we've got array literals. We have dictionary literals, so we can do our mappings like this. So, any self-respecting modern language will let you do this sort of thing. What have I done wrong? Didn't put the equals in. So it's good to know that Swift has it all. Now, interestingly, if we reference into that dictionary, so you can see, well, we've looked up 1 and got a value back. It looks like it's returned an integer, but if we assign that to another variable here, let it catch up again. There we go. If we inspect the value of that, yeah, you can't read that again, but it's actually telling us that the type of x is int question mark. You may be familiar with this from some other languages, but if not, it might look a bit unusual. In fact, if we create a new variable here, let's make that a var actually, we can give it the type, say, string question mark. Wait for that to catch up, and it's giving us a nil. We can go back and, with that dictionary, do something similar. Here's a miss on the dictionary. It gives us a nil. So this looks like we've got pointers going on, but actually Swift doesn't have pointers, at least not that are accessible at this level. It's a very safe language. What this is an optional type. And in fact, that question mark is just a syntactic shorthand for an optional of string. Gives us the same thing. So we can now assign that to give it a value. Really can't type this morning. So now it has a value. So that's good. But then how do we work with optionals? If we want to do something with the value, well, we could test it with an if statement. Like this, we can compare it against nil. And then we might want to say, print it if we have it. That works. It's a bit clunky. It's not particularly safe. And now we can say that it's evaluated to this string with optional in the name. That's probably not what we wanted. So we want to get the value out of the optional. And we can explicitly unwrap the optional by putting the exclamation mark or bang symbol on the end. There's a reason that symbol was chosen, because it looks like a warning. There's danger here. If you're using this in your code, you should probably think about whether there's an alternative way of doing it. And there is. So you can do that, but so if we didn't have the if statement there, and we didn't have a value, that then blows up at runtime with a hard error that's going to terminate your program. So don't do that. What we do instead is we can use something called an if-let. And what that does is, if the optional has a value, our bound variable in the let now has that value unwrapped safely only within the scope of the condition. So now we can safely print it there. And if I, again, remove that, it's not going to go into the if statement. So that's a much nicer way of doing things. Now, optionals are really important in Swift. They're actually quite a big deal for people who came from the Objective-C world, and they're still coming to terms with it. But it's a really safe way of interacting with things that may or may not have a value. So there's actually a number of different ways that you can deal with optionals in Swift. I'm going to show a few sort of as we go further through some later demos. Just one more I want to show now. It's called optional chaining. So if we look back at that string we had earlier, so this is just a string, not an optional. We can get the characters and get the counter characters on there by calling a method. That's how we do that. Now, if we wanted to do that on our optional string, well, we could explicitly unwrap it and then get characters.count. But of course, that will blow up if it doesn't have a value, as we have there. What we can do instead is we can put a question mark on the end of the value. And that will now say, if we have a value, now carry on and call the method on it and so on. If we don't have a value, we skip the rest of the expression and just return a nil. That's why we got the nil there. So if I put that value back in, we now get the value. It's simple, it's safe, and you don't actually need to know that this is technically an example of a monadic binding built into the language in a hard-coded case. You can just benefit from what that gives you instead. There are ways of doing monadic binding more explicitly if that sort of thing interests you. We're not going to cover that too much. We'll touch on it a little bit later. But there's a number of features like this sprinkled through the language to really make working with optionals safer and convenient, which is quite nice. So that was the first demo, just to give you a little taster of some of the fundamentals of the language. We've just been dealing with values so far. I'm going to go straight into another demo where we look at functions. So let's define a function to just say hello. So I'm just going to print something to the console. So pretty simple, no arguments, no return value. We use the func keyword to introduce the function, and we can call it much as you might expect from most other languages you'd be familiar with, and certainly not like Objective-C. Not too many surprises there. So let's parameterize that now with an argument. So let's say name, make that a string. Of course, we have to annotate the type here. We can use string interpolation here now. And you might expect that we can just pass the string to the function like that, but we can't. It's saying we're missing the argument label. Again, we'll accept the fix-it. So we have to label our arguments by default. This appears like you may have seen in some languages that have the optional named arguments. It's not quite like that. This traces its lineage back to Objective-C, where the labels for arguments are actually part of the method name. In fact, you insert the arguments into the signature of the method. It's a really weird thing that most people new to Objective-C really struggle with. They made it look a bit more familiar in Swift, but it's still the same thing going on. You have a bit more control, though. So we can actually suppress the need for a label if we put an underscore up there, so we can do that. Or we can give it a different name. I'm going to think of a better example. We can do that. So we've got some control over it, but by default, we have to name our arguments. And this might seem a little bit of a hassle, but what it does is it forces you to make your methods much more readable. And I'll hopefully build this up into an example that shows that in a moment. So if we, in fact, yes, that was the one that I meant to do. So that works now. So what I've done here is we've actually given two names to the argument. So the first one is the external name. That's the label. The second name is the internal name, the name of the argument coming in. Look how this reads. So the function definition is say hello to name. Hello name. And now the call is say hello to Oslo. It reads really nicely. It doesn't always drop out quite so neatly as that, but actually very often it does. It's actually a really nice property of the language, sort of forces you to write things in a way that makes things more readable in natural language. So going to add another function now. Let's say make greeting. And this time I'm going to parameterize the greeting itself. So it's another string. And then I'm going to have a name again. And this time we're going to return a string as well. So we use this arrow syntax after the function to say what we're returning. So now I'm going to just build the string, again using string interpolation. And now I can use that in our say hello function. I've suppressed the first argument label, so we can just say hello there, and then pass name. That should work. It doesn't. What did I miss? Oh, I missed the second label. But there, it's all working. So now we're seeing a function with 2 arguments. We've got suppressing a label, including a label. We've got a return value. So we're seeing most things that we can do with functions now. Interesting with the labels, but otherwise nothing too complex yet. So let's go a little bit further on this. For our third demo. And for this one, I'm going to build up an array of language names. So I did a talk on C++ yesterday, so we'll include that. I'm doing a talk on Swift now. We'll include that. I work at JetBrains, so let's put Kotlin in there, because why not? I said earlier that F# was one of my favourite languages. Let's include that one. And, of course, we'll put Haskell in, because that just makes it sound more impressive. So we've got a list of languages. Let's see what we can do with that. So we've got a method sort here. Now, if we try and call that, that's going to give us an error, because actually the error in this case is not so helpful, because what it really means is that this is a mutable method. We've used let. If we change that to var, this will work. It will sort in place. The big part of the changes in Swift 3 last year was sort of formalising this idea of mutable and immutable functions on objects. So if you've got sort, then you can predict that there will also be a method called sorted that will return a new array. In fact, that's exactly what it does. As we can see here, we've got our sorted array. But now we've got a problem, because this is the talk on Swift. But we've got C++ first. Swift is actually last in the list. That's not what we want at all. So let's see if we can fix that. Obviously, we want to sort the other way. So if we come back a little bit, we can see from our code completion that there's another form of sorted that takes a function called by, which takes 2 strings and returns a Boolean. So we can clearly see the signature of this function that it takes. So let's try and use that to sort our languages backwards. So one way we can do that is to write a function here, like we did in the last demo. We said it's going to take 2 strings. Got S1 and S2, and return a Boolean. And all we want to do is just provide an ordering between those 2 strings. And now, sure enough, we've got Swift first. That's what we wanted. So that's great. That's what we wanted to do. But what year is this? We had to write a full function there. Surely this language has closures, or lambdas, depending on what you call them. And of course it does. So how can we use that? Let's grab that function, and I'm just going to drop that straight in. It's not quite right yet. Also, we can get rid of the func keyword and the name. And now we just move that opening curly brace back to before the list of arguments, and replace it with the in keyword. And that's our lambda. That should now work. It does. So that's nice. So we're getting somewhere. We're not saving a lot yet. There's still quite a bit of code there. But now we've got this lambda in context, presumably we can take advantage of that type inference and clean this up a bit more. So we know that these must be strings. So yeah, we can get rid of those. Don't need those annotations anymore. Same with the return type. We can get rid of that. And in fact, once you've done that, if the body of the lambda is just a simple expression, you don't even need the return keyword. So we can get rid of that as well. In fact, if I put that, I'll put that on the next line. So we see the whole thing. By the way, I would put this all on that line, but then it obscures the evaluation on the right. So I'll keep that down there. So we can also, now we've got rid of the types, we can get rid of these round brackets as well. That's starting to look quite clean. In fact, I would be tempted to stop there. I'm quite happy with the readability of that. But if you want, you can go further. So one thing we can do, because we've just got two strings there, we immediately use them. We can just do that with positional names. We don't need to introduce new names here. So $0 and $1 gives us the first and second argument, respectively. So we can get even further. Now you might be thinking at this point, surely that's as far as you can go. We've got some more tricks. Closures or lambdas are so important in Swift that there's a number of special cases to handle them. So most often, if you've got a lambda as one of the arguments, it will be the last argument. And where it is, you can put it outside of the round brackets. So lose the label as well. So we could do that. And if there are no arguments, we can also get rid of the round brackets. So we're almost at the limit, but not quite yet. We can go further. So let's get rid of that for a second. Go back to our code completion. So we saw that what we actually wanted was a function that takes two strings and returns a Boolean. And what the function is going to do is provide an ordering on those two strings. We already have a function that does that in the standard library. It's called greater than. So we can do that. I would probably not do that. I was happy where we were earlier. But I think you can see how important lambdas are in Swift. There's lots of different ways that you can do them with different degrees of expressiveness, verbosity, depending on what fits the context that it's in. It does mean that Swift is not a simple language. There is extra complexity because of these different ways of doing things, but you get a lot of conveniences for the very common cases. So again, shows you a bit of the character of the language, what it thinks is important. Okay, how are we doing? Got a bit more talk about on the subject of optionals. Let's bring our maybe string back again. That was what we had earlier. So another thing we can do, now we've looked at what we can do with lambdas, there's a method on all optionals called map that if you've worked with any functional language or modern language, you should know exactly how that works. And now you can see how we can use that in a very succinct way. I'm going to use the in syntax here and just print the result. So when we map the optional, we'll get the unwrapped value in the map. We can use that to print it. But if you have used a functional language, you'll be really cringing at this because we've put a side effect in our map. You should never really do that. What you should be doing is computing a new value. So let's do something like that. Instead of printing it, let's lowercase it instead. If I put that on the next line, you'll see the evaluation. There you go. Now we've got a lowercase string. So using map here is not buying as much. It would have been much cleaner just to use an if-let or optional chaining even would have done it. So let's look at what else we can do. I'm going to introduce an integer. Now, the constructor for integers, there's a constructor that takes a string. So we can pass a string to an integer, and it will automatically convert it for us. Or at least it will when that catches up. There we go. But again, if I hover over and inspect the type, that's telling us that it's an int question mark. So it's returning an optional, which makes sense because we can put a string in there that's not an integer, like this one, and then we get a nil. That's what we would expect. So let's now create an array of strings that we want to interpret as numbers. So we can't have a code demo without the Fibonacci sequence, so let's do that now. So now we can map our array by that's right, we want to convert it to an int, didn't we? Yeah. So I use the positional arguments again. So let's put that on the next line. I'll do it this way. Ignore that. Right. Okay. So that has done the conversions, but now each item in the resulting array is an optional, and every item has a value. So that's probably not what we wanted. So let's map again, and well, we know we can explicitly, whoops, wrong currency. explicitly unwrap the optional like this. Now we've got our integers. So that's good, but we've got an explicit unwrap. What if we throw a spanner in the works? Now, of course, it blows up at runtime. So what we can do is we can add a filter in there and say only continue if we're not equal to nil. Now that all works. We filtered out the things that are not integers, and we've got our array of mapped integers at the end. So that's quite nice. In fact, that's such a common pattern that there's a name for it in the functional programming world, and Swift provides just that method. It's called flatmap, and we can do this. Oops. That gives us exactly the same thing in one step. So flatmap will effectively flatten like a two-dimensional view of your resulting data. So that's some fun things that we can do with functions and lambdas, as well as optionals. Hopefully I've got time for this next quick demo. Going off a slightly different tack now. And for this demo, I want us to imagine that we're writing a tool to help us to organise conferences. So we want to take talk submissions in. So let's imagine that we have an enum for a session type. And let's say you do enums in Swift. Use the case keyword, but it's otherwise much as you would expect. So let's have, say, a keynote, a sort of normal track session like this one. And we might have lightning talks as well. So we're sort of starting to build up our model here using enums. So nothing too surprising yet. So let's now imagine that we have an instance of one of these. Let's make this one a keynote. There, much as you'd expect. So now let's imagine we want to write a function that will give us the length of a particular talk. So I'm going to take one of our session types and probably return an integer. So now we can do a switch on the enum. Oops, wrong casing. And again, this looks much as you would expect. So we've got each of our cases. We're going to return, let's say a keynote is a 60-minute time. Track sessions. Some conferences I go to, the track sessions are actually 90 minutes. So let's put that in. So we've got a different time there. And lightning talk, make that 5 minutes. So now we can call that function to tell us how long our talk's going to be. What did I do wrong there? Oh, didn't. Let's suppress the label. So yeah, tells us the keynote's 60 minutes. That's fine. Let's put track session in. That's 90 minutes. But you might not be familiar with conferences where the talks are 90 minutes. And in fact, a lot of conferences have different lengths for the track sessions. So the ACCU conference I was at just a few weeks ago, they do 90-minute sessions and 45-minute sessions. So how can we build that into our model? We could just put some extra instances in our enum up here. We can have a 90-minute track session, a 45-minute track session. But now we're sort of conflating two different things because we'll often want to just decide whether this is a track session or a keynote or a lightning talk. And then other times we want to get the length. We want to keep those two things separate. It'd be nice if we could sort of associate a bit more data with the enum value itself. And in fact, we can do exactly that. So in this case, we might want to say, well, if it's a track session, we've got an extra integer now that's going to give us some more data. So now, in our declaration down here, we can construct it with, let's give it a 45-minute track session. Now, it's still saying it's 90 minutes at the bottom because we haven't changed our talk length function yet. So you don't have to worry about the the associated data here, but if we do want to, we can actually bind that value directly out in the case statement and return that. And if you've used the language that has pattern matching, you'll recognize this as a pattern match. So switch statements in Swift are actually full pattern matches, and enums are actually discriminated unions, or arithmetic data types. So that's quite good, but now we can do things like, I can create a 37-minute track session. Well, that's probably not what we wanted to allow either. How can we sort of get back some safety that we had with the enum of only being able to construct the values that we wanted? Well, we can have another enum for session length, and I can put just the cases that we support in there. Now, we can't have numeric cases, but if we just use a leading underscore, we can fake it. So let's say we want to have 15-minute, 45-minute, and 90-minute sessions. Now, instead of an integer here, I can just put session len. Down here, well, I could say session len dot, let's say 45. But actually, because we know what type we're passing in, we can use type inference, and it will infer the type of the enum itself. So we can use this shortcut where we just say dot. But we were using that in the case statement as well, by the way. So we're not quite done yet, because we need to fix up our talk len. Now this is an enum. We'll need another function to deal with that. So let's call it len. Oops. That was right, wasn't it? Yeah. So this will return another integer. And we've got much the same, whoops. Much the same thing going on here. So 15, I'm just going to return 15 minutes. I'll cheat, copy and paste. Now we can just pass on to that function here. That should now give us what we expected. So yeah, we've got 45 minutes. We've got 15 minutes. And we can do the same with 90. So it's important to actually follow what's really going on here. Forget the language features for the moment. What we've been able to build is an exact model of our requirements that only allows us to construct values that are valid. If they're not valid, it just won't let us construct them. So it's a concept called correct by construction. Arithmetic data types and pattern matching give us really powerful ways to build models that work that way with just a little bit of effort. So if we get time, there's some refinements we can make to that code to come back to it. But I wanted to go back to slides for a second. I can switch that back. So, that's the one. Here we go. Because we showed values and expressions and the functions, some functional programming techniques, and all of this does tend to support this idea that Swift is a functional programming language. But is it? What does it actually mean to be a functional programming language? So did anyone here come to my functional C++ talk yesterday? Yeah, one or two people. Because the next slide will be familiar, because I did the same thing in that talk. I quoted from the Haskell wiki for a definition of what functional programming actually is, because it may not be what you expect. It says there that functional programming is a style of programming which models computations as the evaluation of expressions. That's actually the central defining concept of functional programming. And a bit further down the same page, clarifies a bit more. In functional programming, programs are executed by, again, evaluating expressions. In contrast with imperative programs, where programs are composed of statements, which change global state when executed. Functional programming typically avoids using mutable state. So it's this interesting contrast between expressions and statements. And if you look at Swift, as a language, Swift has statements. Things like if statements, switch statements. I went into this more in the C++ context yesterday, but basically this prevents it from being a true functional programming language. So it's definitely a language that's borrowed a lot of techniques and concepts from functional programming, has good support for immutability, but as we saw, it's not really favouring immutability as such. So it's a pragmatic language that tries to strike the line down the middle. We see this in a number of modern languages, like Rust and Kotlin as well, very similar, sort of giving equal weight to sort of OO and imperative styles and functional programming styles. And Swift is much the same in that respect. But we haven't really looked at the OO side of Swift yet. So I think I've got time to do some OO demos. So let's go back to the playground. And yeah, starting with this one. So we haven't looked at classes yet. So that's actually the next page. Let's come down here and imagine that we're going to continue this idea of something for modeling conference talks. And we're going to create a class for session. So familiar syntax, I'm sure. But actually, before I do that, I'm going to create a struct as well. So what's the difference between a struct and a class? Depending on which language you have familiarity with, you'll have a different answer to that. So in Swift, it's much like in C#, certain other languages as well, where structs declare value types and classes declare reference types. So it's a strict difference there. So structs are typically immutable, though they don't have to be. And they have a set of values. So it's our session type that we looked at earlier. And I'm going to put some other information in there as well, like title and who the presenter is. So because those are all lets, that means we have to construct our struct in a fully valid state. And in fact, if we don't add a constructor explicitly, we'll effectively get one for free where we just populate it using the same names. So let's create one of those down here, like this. So now I can say, should be type. Let's make that a 45-minute, maybe a 90-minute track session. The title is Swift for the Curious. And presenter, funnily enough, is me. So, have I got something wrong there, or is it just catching up? Did I miss? Not a valid floating point. Why is that not? Oh, I didn't put the underscore. That's it. That should catch up now. I think it has, yep. So we created our info. So now we can put that in the class. So we're going to use let again there. So to create a session, you already have to have that info. So that info is what a presenter would typically submit during the call for papers for the conference. But then you'll have additional information that won't be known initially. For example, the date that the presentation is going to take place. So we'll make that optional, make it a mutable variable. So now we can, we need to add a constructor to this. So constructors in Swift are called initializers. Let's use the init keyword. Otherwise they look much like functions that don't return a value. and we can refer to self to disambiguate between arguments and member variables or fields. So should be reasonably familiar for anyone coming from most object-oriented backgrounds. Nothing too interesting just yet. So now we can construct one of those. Like so. Catching up again. And date. Ah, yes. So to use date, I need to import foundation, I think. So let's say a library type. Yeah, that's done it. So we have our session with a date. So at some point, obviously, we do know what date we want to schedule that talk for. So I'm going to fill that out. So we can say session.date equals, and then you'd expect the date class to have some nice friendly constructor that we can make a date with. But it turns out not, because the date class actually comes from the Objective-C runtime, originally NSDate. It's a very old class, and it's not particularly friendly. So we've got things like time interval since 1970. And I can't really do that calculation in my head very easily these days. So, yeah, you can find some code online that will do the conversion for you. If I remember rightly, I should have it in these clips somewhere. That's the one. So there we go. I got this from Stack Overflow. Let's fix it up a little bit. Don't need to worry about what's going on here, just that it works. It's the main thing. So it takes a string and returns an optional date. So now we can say make date and give it a string with what's the month? It's the 6th, isn't it? We need from string. And that should, yep, give us a date. I'll put it on the next line again so we can see the evaluation. In fact, there we see it. That's, I think, today's date. Tomorrow's date, actually, isn't it? You get the idea. So, yeah, we can do that, and that's fine. But if we're working a lot with dates, it's a bit cumbersome having to use these helper functions. It'd be nice if that was actually built in as one of the constructors of date. And we can actually extend the date class to do exactly that. So I'm going to say extension date to extend it. And you might see in extension methods in other languages like C# has a syntax very similar. Usually you can only add additional methods, but here we're going to add a constructor, which is less common. So we'll make that in it. But remember also that our method wants to return an optional. How can we add that to a constructor? Swift has something called failable constructors. So init question mark, when you construct one of these, will actually give you an optional of that type. So we're almost done. And this is where it gets a little bit weird. I'll have to check my notes to even remember the syntax. But what we need to do in a failable constructor is either forward on to another initializer or return nil. So it's a little bit weird. We're either returning something or not. So if we say let date equal this bit. So we've constructed our date. Now we can forward on to another constructor. And we'll have to use this one because it's time interval colon. So since time interval 0, this date. Yes, that's what I missed. If we've got a date, we'll forward on. Otherwise, we'll return nil. So, like I say, it's a bit cumbersome. One of the little warts of the language that I was hoping they would have sorted out by now. Is that going to work? And now we can actually use the date constructor instead down here. Is that still catching up? And there we go. That does seem to have worked. Can't see the date in there now. So we extended an existing library class with a new failable initializer and just a few lines of code. I think that's quite a nice property. And another thing that we can do, I won't do all of this, but we had our helper functions for our enums earlier. What we can actually do is make those members of the enum. So enums are first-class types like classes that can have methods on them. So now, rather than passing in our session length, we are one. So I can just say self here. And that should work as before. In fact, we can go a stage further and we can also inherit interfaces on an enum. So if we implement custom string convertible, standard library interface or protocol in Swift terms, that has one method. It's actually a property called duration. And this is the syntax for a property. If we do that, then this enum automatically becomes convertible to a string. To an integer. That's not the one I wanted, was it? Okay. Yeah, getting ahead of myself. But we can write that as a property. And now we can come back down here and instead say return length.duration. So I'll skip over the custom string convertible bit, but enums can conform to protocols, and you can also extend enums in the same way that we saw with date. So there's actually really good OO support in Swift with extensions. You can even extend a type, an existing type, to implement a new interface. It's actually something that I've not really seen in any other language, which, if you think about it, is a really powerful concept because it allows you to take a type that has one interface and make it conform to some other interface that wasn't intended at the time. It allows you to make different types work together, even though they've been written entirely independently. So I don't think we've got time to show that one now, because I wanted to get onto one more demo, because this one's quite fun actually. I'm going to bring up my snippets again to see this one. So let's find that. Here's the one. All right. So this is based on a sample I found in a book, and I thought it's quite a nice example to start with. So what it's doing is it's using the Google Suggest API. So this is going out to the network, to the internet, to look up search terms in real time. So I've commented some of this out because some of this is going to cause a problem. In fact, let's put that in for a second, because there are some problems with this as it's currently written. So what I'm going to do is call this this function with a string. So let's put our search term as why do. And now, look, you can see on the right-hand side, it's actually evaluating this by going out to the internet and getting the top search terms for why do. Not particularly good ones today. Sometimes they're a bit more fun. We could put anything we want in there. But what happens if we don't have internet? Let's turn the Wi-Fi off and force that to refresh. Now it falls over horribly because there's no error handling in this. We've got a number of things going on. We've got parsing of URLs. We've got calls out to the internet. And then we've got parsing of JSON coming back. There's all sorts of places this can go wrong. But we're just not handling it at all. So what we could do is, say, take this one where we are constructing a URL object. This is the first place it can go wrong. We could put an if-let around this because it returns an optional, rather than that exclamation mark at the end. Then we're going to have to indent everything underneath it. And then we'll go on to the next one, and we're going to indent that as well, and so on. And we get what a lot of people call the pyramid of doom, or the arrow of doom, where everything just gets indented for the sake of the error handling, which is not really what you want. So instead of if-letting, we can use another construct called guard-let. And this works the other way around. It says we'll continue on if we've got the value, else we'll do the error handling bit. So let's return, we're returning an array of strings, so I'll return an empty one. And we can do that with all of these. So we've got another exclamation mark there we can get rid of. And again here we've got a few of them actually. So I'll convert that to work with optionals. And then finally, getting the result out. We're assuming its position. So the as keyword is doing a cast. Right. That should now work. What did I miss?
Else on line 18.
Expected it. Did I miss an else? Yeah. Here. Still missing something. NSRA not unwrapped.
Missing round bracket?
Is that one? No. Not quite sure what I missed there. Let's put that back. I think we need to split that up. Okay. That's now working. It's airing out here. So we've got our empty string. But maybe we want better error handling. Rather than just returning an empty array, we want something that tells us what actually went wrong. So Swift has something that looks like exceptions with many of the same constructs, but it's not exactly what you'll be familiar with in most other languages. And in fact, in a way, it's more of an encoding in the language of the result monad that functional programmers may be familiar with, made to look like exceptions. So the first thing we need to do is put the throws keyword on the function. So it's part of the function's type, or its contract, to say this function throws an exception. And that means that the call site now has to handle that, and it won't compile if you don't. So you have to say try, make that call for it to compile. That's not compiling. Freeze mainly, put it the wrong place. Okay, goes there. Now actually what try will do is it will propagate the exception if it's thrown. But there's two alternatives we can also use. We can use try question mark, and that's interesting because that will convert the exception to an optional. So if we don't want to deal with exceptions, we can stop it at this point. Or we can do try exclamation mark, and that will be a hard error at this point. So we've got quite a bit of scope for what we want to do with that. So going to go with just try. And then we can put a throw here. And what we'll throw is an enum type that implements error. I'll have to give it a few cases. Because this is an enum, we can have associated data if we want. I'm not going to do it here. But we can say what our different error types are. So I'm going to throw that query error. And this is it's a network error. And that should now throw the network error. To catch it, we put this in a do catch block. And then the catch itself supports pattern matching. So obviously I'm rushing through this a bit just to hopefully demonstrate the power. And of course we can just have a catch-all as well. So it does look very much like exception handling that you'll have seen in other languages, except that you're always forced to deal with them. You have a number of different options for how you deal with them, and the compiler will enforce that you're doing the right thing at all levels. And you get the power of pattern matching for unwrapping them. So this is not like checked exceptions in some other languages. This is a better alternative that does actually work, at least in everything that I've thrown at it. As you've seen, we've just done a networking demo at a conference, and it's worked both ways. So that's the power of Swift. That's the last demo. I think we're getting to the end. Did I have a last slide? I did. It's just this one, where I want to say thank you for coming, for listening. And all of the code that I showed, I put in a playground on GitHub. So that's the GitHub repository for it there. Or you can follow me on Twitter. Thanks for listening. Have you got any questions? Yeah.
What's Swift written in?
Sorry?
What's Swift written in?
What is Swift written in?
Yeah.
C++. Right. It's not yet self-hosting. I don't know if there are any plans for it to be self-hosting, but it's certainly written as or designed as a systems language. So there's no reason that it couldn't be. It just isn't currently. Okay, yeah.
Is there a support for async?
Sorry, support for async, did you say? Not yet. That's something that's on the cards for Swift 5, I believe. We're working on over the next year. It was going to be Swift 4, but they pushed other things ahead of it. But on the platform itself, on Mac and iOS, there is basically a C API that's not bad called Grand Central Dispatch that gets you part of the way there, but it's still a bit more manual than a full async monad. But that's definitely something that's on the cards. So good question. Yeah.
Which platforms can you run Swift on?
Yeah, very good question. I did mean to bring that up when I was talking about the open source. Because it is open source, you can actually build it on any platform you want, but there's an official maintained port for Ubuntu, and that's used quite extensively by IBM. They're doing a lot of Swift on the server, and they're building out some of the frameworks for that. There's a web server written in Swift that IBM maintain. It's early days on the server. It's not a complete story there yet. In fact, the async stuff will really play into that, but it's looking promising. Yep. Okay, so I think if you've got any more questions, you can come and catch me afterwards. Thank you.